This is an example video for using the first derivative to find the behavior and extrema of a function using our knowledge of critical points and the relationship between the original function and the first derivative of the function. We will go through an example numerically and graphically using the chart that explains this relationship. The chart is as follows.
I see that this chart includes the function behaviors and critical points, but where does extrema fit on the chart?
That's a great question. The extrema will be at the critical or undefined points, and then we will use the behavior of the graphs to determine if that critical or undefined point is at a local maxima or minima. Let's look at a problem to make this process more clear. Find all local extrema of the function f of x equals x to the fourth plus 3x cubed plus 2x squared plus 1, and where the function is increasing and decreasing. To determine the x value of the critical points, we will need to determine where the first derivative is equal to 0, and we will also need to know if the graph changes behavior at those points. Our first step will be to take the derivative of the original function and set it equal to 0. Then we will solve for x algebraically by factoring and using the quadratic formula. Now that we have determined the x coordinates of the points where the derivative is equal to 0, what do you think the next step will be?
Well, since we now know where the extrema may be, we need to determine if they are a local maximum, minimum, or not extrema by looking at the behavior of the function.
Exactly. We now need to determine where the graph of the original function is increasing or decreasing. This means that we will examine the y values that correspond to each of the x values that we found above. To do this, we will use a helpful chart. On this chart, we will keep track of the behavior of the original function between each of the zeros of the first derivative. To do this, we will start with a number line with each of the zeros of the first derivative. Then we will choose points in between each of the zeros of the first derivative. For this, we will choose -2, -1, -0.5, and 1. Then we will plug in these points to the first derivative function that we found at the beginning of this problem. You may want to use the table function on your calculator to do this. Based on this, we know that from -infinity to -2, the first derivative is negative. From -1.64 to -0.61, the first derivative is positive. From -0.61 to 0, the first derivative is negative, and from 0 to infinity, the first derivative is positive. We know this to be true because the graph can only change behavior where the first derivative is equal to 0 or undefined. In this case, we had no undefined points. We know from the chart at the beginning of this video that when the first derivative is negative, the original function is decreasing, and when the first derivative is positive, the original function is increasing. Knowing this, what can we say about the original function?
We know that between -infinity and -1.64, the function is decreasing. Between -1.64 and -0.61, the function is increasing. Between -0.61 and 0, the function is decreasing. And between 0 and positive infinity, the function is increasing.
Correct. Now we can use this information to determine where the maxima and minima of the function are. It may help to make a rough sketch of the general trends of the original function to understand this. We can see from this that each of these points are critical points because the graph changes behavior at each point. When the function changes from decreasing to increasing, the critical point is a local minima, and when the function changes from increasing to decreasing, the critical point is at a local maxima.
I get it. That means that the point -1.64 is a local minima, -0.61 is a local maxima, and 0 is a local minima.
Exactly.